Welcome back again to our discussion of the F block metals, actinides and lanthanides. This is part 2. This is the second recorded presentation. And in today's presentation, we're going to talk about the oxidation state of lanthanides and actinides, and also a bit of the color chemistry or the electronic spectra of lanthanides and actinides. First, we want to remind ourselves about the electronic configuration of the lanthanides and actinides in the non-ionic state, and remembering that the electrons are filling the N-2F shell, the 4F shell. The last electrons are actually going into that shell. In some cases, in lanthanides, we actually have the 5D shells being filled for cerium, gadolinium, and also for lithium. And you should make yourself familiar with these configurations so that you can work out the configurations for the charged species. The ones for the actinides are given here, and they follow a similar pattern, so you can refer back to this. It's good if you can write down the configurations of the +3. Why we're using +3? Because as we see, the +3 state is normally the one that is most stable for both the lanthanides and the actinide groups. So in the lanthanide series, the most stable oxidation state is +3, those series. That is, we lose any of those s electrons, and in the case of 3, I point out the electron, and then we begin to lose stuff from the 4F shell. So in all of these cases, we see the +3 state is most stable, and as we go from left to right across the table, we realize that other oxidation states aren't really as stable at all, and this tells us that the stability of the +3 state increases as we go across the table, and that is also linked to the fact that the size of those ions are also steadily increasing. So the effective nuclear charge is also increasing, meaning that when that state is formed, there is a lot of that positive charge from the nucleus actually being felt a lot more in those later lanthanides than the ones in the earlier lanthanides, and so the +3 state is most stable. There are some deviations where we get +4, even +2, but they aren't as pronounced as in the actinide series. Now the +4 and the +2 states, for example, are found and are said to be there because of some stability that is offered if we have a half-filled shell, so that's 7 electrons out of 14, or the filled shell 14 out of 14. So in the case, for example, of cerium +4, there are no electrons in those outer shells, and that state is actually quite stable. Of course, it will be isoelectric with xenon, right? In the terbium example, there's a F7 configuration, so it means each of those suborbitals in the F shell actually have 1 electron. This is half filled. Of course, they're all paired. When we look at 2 other cases of the +2 oxidation state, in one case we have a 7, so of course half filled, or 14 that's filled, and those offer some extra stability to allow those materials to remain in those states. Of course, the ones in between these examples that we've given won't be able to satisfy that configuration arrangement. And as we saw when we looked at the change of the ionic and the metallic radius, we saw this particular one, for example, coming up out of the range. In fact, these two, and of course that is again because of the stability afforded by having a fully half-filled or fully filled subshell. The actinide series is slightly different because, as you can see, there are a number of oxidation states which are found. As we go from left to right, we realize that we lose the ability to have any of the higher oxidation states, which tells us that the +3 state is more stable for these materials as well. The plus 4, 5, 6, and 7 states are found here. And this really has to do with the energy difference between the 5F versus 6D for the actinides versus the 4F versus 5D for the lanthanide series. And really the energy difference here is lower, and therefore it's easier to take out that electron and make those states, high oxidation states, stable, as opposed to in the lanthanide series where those energy differences are larger, and therefore if we're trying to remove those electrons, 5 high oxidation states, we'll have to add a lot more energy into that system. Of course, as we go further towards the right of the table, this is not the case, because remember the atomic size is decreasing, the extent or effect of that nuclear charge is increasing on the outer shells as the atomic size decreases due to the contraction, and we're getting larger and larger ions as well in terms of larger atomic numbers, higher atomic numbers, and therefore that effective nuclear charge is becoming more effective, right, because of the low shielding ability of those F electrons. So it means that over here it is not as easy to remove those electrons to get high oxidation states. So these ones, I suppose the early or the mid, I should say the mid actinides are the ones that have the high oxidation states. There's some oxidation states, for example, like the +2 state here. And this one is only stable in particular conditions, right? In fact, it's only stable when we have calcium fluoride salts around to stabilize the structure. Of course, this means that going from one oxidation state to the next, or the redox chemistry, is not as profound as in the case of the 3D transition metals for the lanthanides, but probably is more common or more profound in the actinide series. So we talk about oxidation states. Now we're going to talk a little bit about electronic transitions, and you'll already be aware with types of electronic transitions which give rise to different peaks in your, for example, your UV spectra, different absorbances and or emission spectra. And in this case, for the lanthanide and actinide series, all of the transitions are active. So we have FF transitions, which you know are forbidden in the case of lanthanides and actinides, because in their complexes, those transitions have the same the same state. So they're going from a grad to grad or ungrad to ungrad state. And I'll show you that in a moment. But also we have FD transitions, because we know that the F shells are filled before the D shells, they're filled and they're below the D shells, and so we kind of transitions from the F to the higher lying D shells. And of course, ligand to metal charge transfer. This is an interesting property, but really more important for the higher oxidation states, where the metal can accommodate extra electrons from the ligand, right, more easily. Of course, the high oxidation states are also those that are larger in terms of size as well. And so these three are the transitions that give rise to the spectra we observe. Of course, the first one is forbidden and therefore not as intense and have narrow or sharp peaks, narrow bands on the spectra. These are usually in the visible region. I will show you that the ligands have very little effect on those transitions. However, for the FD transitions, they are loud and they're intense broad bands. Of course, higher energy, because the difference between F and D is higher energy than F and F. For the ligand to metal, of course, these are intense bands and they are allowed transitions, and they're actually affected by the oxidation states and the ligands themselves, right? So, of course, the nature of the ligand will affect the ligand to metal charge transfer. Let's think a moment about lanthanide and actinide that will be in octahedral coordination, having 6 ligand partners, and remembering that we can find the terms, symmetry terms for the f orbitals from the cubic functions in our character table that I circled on this character table, and we can see that one of them will correspond to A to U, and then there will be a group of 3 and 3 orbitals, f orbitals, that will correspond to T1U and a T2U in terms of the molecular orbital diagram. So we could sort of put this in this terminology where we have them now. In fact, they are split. We will consider them as being at the same level, but they are split into these three groups of molecular orbitals that have different symmetries. Now, these orbitals are all in the F, and therefore we remember that because of lanthanide contraction, they are deep inside the atom, and therefore they are shielded from ligand effects. They are shielded because the ligands aren't really interacting too strongly with these orbitals, because they're really feeling a lot of that effective nuclear charge, right? And so these FF transitions are forbidden, because we can see that in these three sets of these three groups here, they are all ungarad in these cases. So because of that, the Laporte selection rule is not obeyed, and of course these will be weaker transitions. They happen, but they are weaker. They're indivisible because the energy differences between these groups aren't that great. Right, the color here is mainly based on the unpaired electron, as we'll see in a minute. That unpaired electron is what is moving from level to level. So where the electrons, for example, there are no electrons, of course we can have no transitions. Where the shells are filled, for example, if we have 2 here and we have 6 here, that's highly unlikely that it's going to move. Where they have unpaired electrons, that's when we're actually going to have movement between them. So if we look at the trivalent ions of the lanthanide series, we can see some of them are colorless because there are no F electrons, or there's only one here that's going to be in an A2U type symmetry orbital, and so it's not going to move very much, and so energy difference is quite small. It's colorless. Then when we go down to the middle, this is the case where we have 7. They are, in this case, this is colorless because that is a stable state, as we said, half filled, and down here, of course, completely filled is also stable and electrons are not moving. In between, we see that the colors go from green, pink, yellow, back to pink, pink, yellow, back to green. And so this tells us that the number of unpaired electrons gives rise to that color. Now remember that if we observe, for example, a yellow or reddish color, that means that we're observing that those wavelengths are the ones that are transmitted, whereas the higher wavelengths are the ones that are absorbed, right? So you would be familiar, and if we see here, for example, yellow versus pink versus green versus lilac, here it means that we're absorbing at a lower level, and of course the higher ones are trying to transmit. We see lilac. When we go from lilac to pink and yellow, of course the energy transitions are smaller because of course these are unpaired. So more or less, the more unpaired electrons are going to give slightly more intense colors, but all of these colors are not as intense as charge transfer or FD bands. Now we can talk about some isoelectronic species. For example, cerium plus 4, as I said, has no electrons in the FD or S. And so it's an F0 situation, but this one has an orange-red color, not because of FF transitions, because there are no electrons in the F, but because of charge transfer from the ligands, for example. Similarly, samarium, that has a blood-red color, is also due to charge transfer in this case. Now it's isoelectronic with this one. It does have F electrons, but the charge transfer is more important. So wherever we see a very intense color, particularly if that intense color is in the orange to red region that we observe, that means it absorbs strongly in the violet to blue region. That is normally a charge transfer case. Then we have some things isoelectronic with the gadolinium and lutetium, and these of course are yellow green in color as well. Now note, this one is colorless. This one here would be colored. So we had an F6 state, and now we're going to have F7 state, but the arrangement of those electrons are not going to be the same in that case, right? Now the actinides follow similar colors to the lanthanides if their electronic configurations match in terms of there are, for example, actinide that's a 3+ ion right below a lanthanide that's a 3+ ion, has similar color. However, the bands are much sharper because the energy between those FF transitions occur at a lower energy value in terms of the difference between the splitting in those orbitals. Of course, remember the actinides are larger in size than the lanthanides, right? And so those outer F shells the splitting there is not as great as in the lanthanides. There's a higher propensity for charge transfer bands, of course, because of the lower energy differences between those F and those F and D subshells as well. And so in general, the actinides show much more intense colors than the lanthanides for their complexes. We talked about absorption, but the chemistry of the lanthanides and actinides are also very interesting in terms of their emission spectra. And in fact, many of the uses of these F-block metals have to do with their emission spectra. And so here we can see that we have some 4F electrons, for example, in lanthanides. If we have FF transitions, we might go from here to there and back down. These are weak. We can have, if we have sufficient energy, such as near UV incident light, we can have a transition from an F to D. We can see 335 nanometers light required for that. It's relatively high energy. But of course, in this case, we can have where we change the state of the ion itself, the excited ion. For example, here we go from a 5/2 to 3/2 state. They're both Ds, of course. And this is a non-radiative decay. So that's sort of a rearrangement or reorganization of those electrons in those excited states. We could see the same thing here in the ground states. That, of course, means that the difference between these states and these states aren't the same, and therefore we can have emission and radiative decay, where the emission spectra or the emission line is going to be at a lower energy than the absorption line, right? And so they emit, and we call that luminescence. And of course, if we have multiple lanthanide actinide ions in close proximity to each other, we can have some energy transfer between them, and we can go from take away some of this energy from here, and these electrons can be de-excited to the ground state in the other species, and then we get different emission spectrum. And this is actually one way in which we can tune the emission spectra, and it's actually how emission spectra is tuned for lanthanides and actinides to do a wide variety of applications. Okay? Now we will look at working out these terms here that you see that may confuse some of you all. When we get to magnetic moments, we'll just do a review of that. But for now, there are two things you need to remember here. The emissions don't match the absorption. That's why we have luminescence, because of radiative decay between the states, right? Excited, and of course also in the ground states. And also we have the ability to have energy transfer, which is really electron transfer from one system to the next, where there are multiple or different types of lanthanide ions or actinide ions in close proximity to each other to allow that. For example, if they were doped into a crystal, right? So if this one was doped into a crystal of that, then we could see that we could have that energy transfer, that electron transfer, and then the radiative decay will not be the same, and we can get different lines depending on where that transfer happened to. And many of these ions, these lanthanides and actinides, have the near IR luminescence. So you can see the variety of luminescence here from all the way. So this is IR is over here, so this is near it, this is near IR, and we can see some of them have very intense and large peaks. For example, this one here in the IR region, and so we could use this for particular type of diagnostic studies, etc. in the applications. Some of them, of course, can luminesce in the visible as well, which means that these will be useful for these ones that luminescent invisible will be useful for harnessing that property of those materials. So to recap, we discussed why the +3 oxidation state is most stable, noting that there are up to +6, +7 oxidation states that are stable for some of these lanthanides and actinides. We looked at the types of transitions that occur, forbidden, and also those which are allowed, and then discuss the intensity of them with respect to each other. We learned also that these F block metals in the ionic states also show luminescence, and that is one of their chief properties, that we're interested in luminescence because of the radiative decay, non-radiative decay in between those states in the excited state, which allows you to have emission that doesn't match the absorption spectrum.